So when we talk about the idea of an indefinite integral, essentially all we're saying is that we're dealing with an integral of some function, but it's not specified the interval over which we're integrating that function. So it's indefinite. We don't know exactly where we're talking about the function being integrated. So we've stated that this generally means the antiderivative of that function f of x, or in other words, the derivative of that big f function would be this little f function. So our relationship still holds. So notice there is a big difference here between a definite integral and an indefinite integral. A definite integral will be a number. So if I calculate the integral from a to b of some function, that's going to be equal to its antiderivative evaluated at b minus its antiderivative evaluated at a. This will be a number. But if that integral is indefinite, then it's just going to be a function. So we're just going to say that this is equal to that big f of x plus c. Don't forget, since we're not actually evaluating something here, we do need to account for that constant. So this would be a function. So that's the major difference here. Definite integrals, like what we've been doing, you'll get a number, but now we're going to start talking about indefinite integrals where we're just going to be left with a function that we need to consider the constant for. So a couple general formulas that we want to make sure we outline before we get started. You're going to see that they're very similar to some of the formulas we've used in the past. So just like with summations and derivatives and limits and a lot of all these other things that we've dealt with this year, if there is a constant within your integral, you can remove that constant from the integral and then multiply it by the integral itself. The integral of a sum of two functions is equivalent to the sum of the integrals of those two functions. The integral of some constant value is just equivalent to that constant times x plus some other possible constant. This is essentially reversing the power rule, right? If I take the antiderivative of some function with respect to that value, u or x or whatever I'm using, and it's got an exponent, then its antiderivative is going to be 1 greater than that exponent, but I also have to account for the fact that the denominator needs to be that same number, so that if I were to take the derivative of this, those two values would cancel, not anything new. And also, we saw an example like this last week. This could be treated as the integral of 1 over u du, right? It's just rewritten that way. And so the antiderivative of 1 over u is going to be ln of u, or if we're talking 1 over x, it would be ln of x, right? So there are a lot of general cases, and we could just go down the list of all the obvious ones that if you see these, you need to know its antiderivative is this. But we've sort of talked about a lot of those different examples. So these three here are more general rules that we are going to apply. And then these two here are more specific examples, but examples that we'll see a lot. So let's do an example. Find the general indefinite integral. So you'll notice we're not told what interval we're integrating over. It's just an indefinite integral here. So I'm going to apply the sum rule there that we outlined on the first page here. And I'm going to say that this is equivalent to the integral of 10x to the fourth dx minus the integral of 2 secant squared of x dx. I'm just going to separate those, which I'm allowed to do according to the properties that we just talked about. All right, and there are some constants here that I could account for, right? So I could pull the 2 out, and I could pull the 10 out from each of those integrals. So this is 10 times the integral of x to the fourth minus 2 times the integral of secant squared. And now I can take the antiderivatives of these functions on their own. So this case here is going to be the power rule, right? I'm reversing that power rule, so it's going to be x to the n plus 1, but I also have to divide by that same n plus 1 to get it to cancel. All right, and then here, it's my job to recognize which function has a derivative that is secant squared, and that's tangent. So my next stage is 10 times x to the 5th over 5 minus 2 times tangent of x. Don't forget that there could be some constant on the end of this whole thing as well. All right, so I can simplify what I've got there in my first term and rewrite this as 2x to the 5th minus 2 tangent of x plus c. Now I could prove that this works by then taking the derivative with respect to x of this function, and I should get that original expression. If I don't, then I've done something wrong. The last example in this video is a little bit less straightforward. It's not obvious what to do with this. But so what I'm going to do is I'm going to separate this into two fractions. So this is the indefinite integral. And I'm going to say of 1 over sine of x. And this is something that we've done in the past with these trig functions. We try to break them apart. So I'm just rewriting what I have there. And when I do that, I'm going to notice that I have two trig functions by their definitions, right? 1 over sine of x is cosecant of x, and cosine of x over sine of x is cotangent of x. Is there a function whose derivative is cosecant of x times cotangent of x? And there is. So the answer then is negative cosecant of x plus c. So just a couple examples of how you might want to rearrange some of these. I'll give you some practice problems to work on before I send the book homework, which will be in the next lesson.